This is the Teratopsis dohrnii, also known as the immortal jellyfish. Under certain conditions, it can achieve an almost infinite lifespan by reverting to its juvenile form. And this is John Alfred Tinniswood, who was born the same year the Titanic sank and has been recognized by Guinness as the world's oldest living man. But even so, he's only 112 years old. Have you ever wondered why we humans can't rejuvenate ourselves like the immortal jellyfish, but instead inevitably age and only live for about 100 years? Hello everyone, welcome to Human Observation Society. If you try searching online for animals that don't age, you'll find that most of the ones reported are amphibians, fish, or reptiles, but you won't see any mammals among them. This isn't just something I came up with after casually browsing the internet. Not long ago, Portuguese molecular biologist Magalhães specifically published an article on this topic in Bioessays, discussing this issue and even proposing the longevity bottleneck hypothesis to explain the phenomenon. Simply put, he believes that the loss or inactivation of longevity-related genes in mammals is no coincidence. It was the dinosaurs' doing. He's not blaming them without reason. After dinosaurs became the dominant terrestrial vertebrates in the Jurassic period 200 million years ago, they ruled Earth until the mass extinction at the end of the Cretaceous period 66 million years ago. Dinosaurs like Tyrannosaurus, Spinosaurus, Stegosaurus, and even the ones your mom yells at you about for not coming to dinner, all had incredible fighting power, each more formidable than the last. In contrast, our mammalian ancestors probably had a really tough time during the hundreds of millions of years when dinosaurs ruled the Earth. If you think about how humans are now the dominant species, and how that's forced wild animals to decrease in number and become more active during the day while reducing their nighttime activity. Maybe back in the age of the dinosaurs, our mammalian ancestors, being the underdogs, had no choice but to hide and only come out at night to look for food. Otherwise, they'd be reminded at any moment of the terror of being dominated by dinosaurs. In such a harsh environment, our mammalian ancestors, if not dying young, at least lived with constant uncertainty about their survival. Over time, natural selection would have favored genetic mutations that promoted youth and vitality, rather than those that extended lifespan. Just like rodents today that live under high predation pressure in the wild, our mammalian ancestors could only adapt by evolving survival strategies focused on rapid reproduction and short lifespans. And during the hundreds of millions of years of dinosaur dominance, early mammals underwent adaptive degeneration due to prolonged selective pressure, ultimately losing many longevity-related traits as some of their repair and regeneration mechanisms were lost. Although after the extinction of the dinosaurs, mammals once again evolved some long-lived species. For example, elephants, whales, and humans. But even the longest-lived mammals age faster than many reptiles. Therefore, Magalhães has twice suggested that the aging seen in modern mammals may all stem from biological constraints left over from the age of the dinosaurs. Some time ago, a team of scientists from Paris, France published an important review in the top journal Cell, summarizing 14 hallmarks of aging. Let's first talk about genomic instability among them. As we all know, 80% of human skin aging comes from photoaging, because the shorter wavelengths in sunlight's ultraviolet rays are responsible. The higher energy UVB can directly attack the DNA in your skin cells, causing DNA damage markers such as CPD and 6-4PP. Meanwhile, the longer wavelength, lower energy UVA can generate a large amount of reactive oxygen species, ROS, in your skin, which can also damage DNA. But theoretically speaking, humans have evolved on Earth for so many years, and since we're mainly active during the day, we should be well adapted to sunlight. So why does too much sun exposure make us feel like we're dying? Some people even like to use this as evidence that humans aren't originally from Earth. Hey, if humans really evolved on Earth, why can't we handle sunlight? Maybe we're all actually aliens, guys. But in reality, this might have to do with our mammalian ancestors losing photolyase enzymes during the age of dinosaurs. Simply put, photolyase enzymes are a DNA protection system. It's a repair mechanism that, once activated by blue light, can directly bind to and reverse CPD damage caused by ultraviolet rays, restoring the DNA structure. In 1949, future Nobel Prize in Chemistry winner, Turkish biochemist Aziz Sanyar, observed that E. coli bacteria, which were on the verge of dying due to UV-damaged DNA, could actually recover when exposed to blue light. Inside the bacteria, a special enzyme was able to absorb the energy from blue light and use it to repair the DNA. This enzyme is exactly the photolyase that we humans lost long ago. In other words, our current lack of resistance to sunlight might actually be a kind of post-dinosaur syndrome. Another example is telomere attrition, one of the 14 well-known hallmarks of aging. As everyone knows, at the ends of your chromosomes, there's something like a protective cap called a telomere, which prevents your chromosomes from falling apart. Every time our cells divide, the telomere shortens a bit, and when it eventually reaches a critical length, the cell stops dividing and begins to age. Death is like a car running out of brake pads. Once the brakes are worn out, their lifespan is naturally over. According to American anatomist Leonard Hayflick, human somatic cells typically divide 50 to 60 times, after which the telomeres are completely used up. This might be related to the evolutionary inertia passed down from our mammalian ancestors, who were selected for shorter lifespans, which in turn limited the potential for cell division and ultimately our own lifespan. So, the fact that our human lifespan is genetically locked might actually be thanks to the dinosaurs. Fortunately, in today's technologically advanced world, aging is not necessarily unbeatable. For example, the well-known anti-aging pioneer Brian Johnson, under the guidance of a professional team, successfully broke the world record for age reversal in January 2023, making his biological age 5.1 years younger. Even in November 2024, his rate of aging dropped to 0.64, which means he only ages 0.64 years for every actual year. You might be very curious, how exactly is so-called biological age calculated? In fact, to find the most reliable measurement method, researchers from several well-known universities in Sweden and the United States have been working on this. Using 20 years of follow-up data, the 9 most common methods for measuring biological age were compared. The results showed that, with current technology, DNA methylation testing has the highest correlation with both the biological age functional decline index and functional biological age, making it relatively more reliable. With biological age testing through DNA methylation analysis, we can not only predict an individual's overall aging status, but even conduct detailed analyses of the biological age of various organs. From the frantic escape in Jurassic burrows to today's quest to fight aging, the struggle between mammals and ancient creatures like the coelacanth continues. From Emperor Qin Shi Huang's blind pursuit of immortality pills in ancient times to Brian's modern use of DNA methylation to quantify anti-aging effects, the exploration has never stopped. The path to longevity for humanity will no longer be shrouded in mystery. Although we don't know exactly when the future will arrive, the dawn of hope is already before us. Finally, if you're curious about the biological age of your own organs, feel free to click the comment section below and try out our Leilang BioAge Aging Test. That's all for this video. Thank you so much for watching. Don't forget to like, comment, and subscribe. See you next time.